Right. Okay. Good afternoon, everybody. It's midday, so it's afternoon. Welcome to a South African Statistical Association special interest group seminar, specifically the Spatial Stats interest group. So myself and Renate and Professor Pravesh Deba run this special interest group. We love it because that's our field and we love spatial stats. Renate is going to graduate in 2 weeks' time. So she's in limbo. She's finished. She's got all the documents in line, but she hasn't walked on stage. So she's doctor in inverted commas, but she will be soon. So when you see her in 2 weeks' time, you have to call her doctor if you see her in the corridor or at conferences, which is very exciting. Renate has been on this journey to become a PhD graduate for many years now. She started a PhD during COVID, so it was a little bit stressful, as was everything during COVID, but I think especially if you start a PhD during COVID. And she's done really, really wonderful work, and you'll see now some of the work she's done. So she's currently a lecturer at the University of Pretoria in the Department of Statistics. She's a permanent staff member from July last year, July, somewhere around there. August, there we go. So today she's going to talk to us in the Spatial Stats interest group on her work that she did during her PhD, specifically focusing on spatial linear networks, which is incredibly interesting. Yes, so I'm going to hand over to Renate. And then if you have any questions as we go along, you're very welcome to put them in the chat, but then we'll have obviously you can put your hand up at the end of the talk as well. We'll have some discussions and allow for some questions. Thank you, Renate. Over to you.
Great. Thank you so much, Inga. Yes, so I don't need this slide because that's my introduction, which has been done. There we go. So I want to start with the background of my PhD and just sort of explain what it was about. So Inga has talked about spatial linear networks, and in my PhD specifically, I was looking at road networks. A spatial linear network is any bunch of lines that's connected by points, by intersections or whatever, and that exists in geographical space. But road networks are probably the most common example of spatial linear networks. So the background to my research is that road networks are obviously very important for general urban development and rural development across the world. And especially in South Africa, because we don't really have, sadly, a very well-functioning train system or anything. So most travel occurs on the road network. So actually assessing the level to which the road network provides people with accessibility or access to different areas is super important, especially also in our context where historically road networks were not designed to promote proper integration of cities. They would have these separate areas within cities where different kinds of people were supposed to live, wonderful. So we're still sort of dealing with a legacy of that, even though, of course, since 1994, there's been much more efforts to integrate urban areas. And especially these days, there's a big focus on designing business districts in a way that people can live close to where they work and so on. But that's still, that does lead to a very heterogeneous road network with very different types of neighborhoods with different road network patterns interacting with each other. So things are confusing, essentially. And of course, we want equitable access for everyone. It's specified by UN Sustainable Development Goal 9, and it's also just common sense that we want everyone to have equitable access. So the problem statement of the PhD was generally just to develop statistical methodologies to quantify the degree to which road networks provide access. Of course, in the context of South Africa, but the problem statement is more general. This does lead to two other mini problems that were needed to actually clarify the original problem statement, which is, so between which things, which points, which areas do we want to quantify accessibility? So what are the origins and destinations of travel? And my PhD looked at regions within a study area rather than specific points. And then the question becomes how to select the regions. And the reason I was looking at regions was because many accessibility studies look at accessibility between specific points, but then it becomes much too specific for our purposes. So they'll do things like, okay, what is the level of access that a neighborhood has to hospitals, specifically hospitals, or schools, or urban green areas, which answer more specific questions. But if you're looking at the overall level of access granted by a road network, you need to be more general in your origins and destinations. And because it's impossible to calculate the level of access between every single point on the map and every single other point, I looked at regions. And then, of course, that becomes, okay, how do we select regions? And in my mind, wanting to select regions based on the road network and the road network structure would give a very interesting way of obtaining regions. But then the question becomes how to do so. So these two secondary and tertiary problems sort of came out of the main problem, and they were all addressed in the PhD. So I had 4 research objectives. Firstly, to develop a statistical accessibility model. Secondly, to determine a test for the homogeneity of road networks. And when I get to that, I'll explain exactly what homogeneity means. But it has to do with the road network structure. I referred to it earlier that road networks have different regions. A suburb looks different from the CBD, which looks different from an informal settlement when you just look at the road network pattern. And homogeneity is one measure that could help to quantify these different patterns. Then thirdly, I wanted to design an algorithm to automatically cluster road networks into homogeneous regions. So that's part of the region selection problem based on the road network structure. And then finally, to use research objectives 1 to 3 to explore the effects of road network homogeneity on interregional accessibility. So basically, how does road network structure, at least one aspect of it, influence accessibility? So I'm going to go through the 4 research objectives in order. They are each associated with a research output, although only the first one is officially peer-reviewed, published, but the others are still ongoing. So each research objective is tied to a paper or a project. So the first research objective, the statistical accessibility model, the problem statement there was to develop a computationally simple algorithm to quantify accessibility between regions. And here I specify administrative units because that was what I started with before I started finding the road network structure-based regions. And the solution combined Markov chain theory and spatial weight matrices, using some ideas of a fairly old paper, which just never really seemed to gain a lot of traction in the literature, but I investigated it and it seems quite cool. So essentially, I set up a spatial weight matrix that quantifies the sort of level of relatedness between different regions, and then did a little bit of manipulation to turn it into a Markov transition probability matrix. And then that means that you end up with a sparse transition probability matrix to get probabilities of moving between different regions. And it, to quantify accessibility between okay. And then just to make computation a lot easier, you can just multiply that matrix a bunch of times to get probabilities of moving between further away units. I've got some examples. So here's an example. This is just the one-step transition probability matrix or spatial weights matrix, same thing in this context. So they would be, let's say I've got 3 regions. They're on the right-hand side, and they are administrative units in this example. And then you'd have some probabilities of going from one region to another, which is what I put on the left-hand side diagram. That's just a Markov chain diagram representing the regions and how the probabilities work to move between them. And then those probabilities go into the matrix at the bottom, And then you can just treat that as a normal Markov transition probability matrix. And I've got a slightly more nicer looking illustration. Basically, how this works then is to get accessibility between non-adjacent regions, like between regions A and B in the sketch. You have to take into account the probabilities of going from A to B through all the possible routes that you could take. And obviously there's a lot of them, which is why it's useful to use a Markov chain approach where you just multiply the matrix a certain number of times with itself, and that then accounts for all the different possible routes. I didn't in this presentation go into a lot of detail of how I got the probabilities, because that's a whole other story, but it's based on the distance via the road network. So you could look at other things like traffic volume and so on as well, which is actually a current project that I'm working on, but it was just very difficult to do in the time constraints of the PhD. So I started with a proof of concept that just looked at distance. And then eventually you end up with the sort of relative inverse travel distance. The reason I'm talking about inverse travel distance is simply because less distance corresponds to a higher probability of moving from one place to another because it's closer. That's how I got the probabilities. So in the end, I would interpret these probabilities as, given that you're starting in a certain ward, or region, on the image there, let's look at A, for example. Given that you're starting in A on your journey, what is the probability that you will go to another area, for instance, B, in a certain number of transitions? So what is the probability that you would go from A to B in 2 transitions? That is, for instance, using the purple route, using the red route, using the blue route, etc. Well, it's 3 transitions in this example. And then the other interesting feature of this is, of course, with Markov chain transition probability matrices, if you take the power up to n of TPM and you let n go to infinity, then if it's irreducible, which it is, it will result in a matrix with identical rows, which are the limiting probabilities in Markov chain theory. And there is actually an interpretation for that as well in the literature, which is that the limiting probability, if we're looking at a spatial weights matrix, is the prominence index of a region, which is the probability that you'll end up in that region after a journey of unspecified length, regardless of where the journey started. And that means that gives you an overall idea of the accessibility of that region compared to all the other regions. It's not a very concrete thing that you can interpret, like saying, okay, the probability that I'll go from here to here in so many steps is this. It becomes a bit more vague, but it does give a very good quantifiable measure of accessibility. So that was research objective 1. Here I'm just showing a very small little part of the application because, of course, that is not the this is part of the paper, but the PhD itself has further plans for this research objective. So in the paper that I wrote for the first research objectives, I specifically looked at wards within the city of Tshwane, and then explored how, if you are going on a short journey of, let's say, 10 transitions versus 20 versus 50, and then ultimately if you let n go to infinity, starting in the CBD, what are the wards that you end up with? And of course, the last image, n goes to infinity, that's the prominence index. To calculate it, I started in the CBD, but those wards in blue there, the highlighted ones, they are the most accessible ones in the municipality, regardless of your origin, because n has gone to infinity. So it's that limiting probability. And then we did manage to publish a paper. So there's more information there, and I've put the reference on the slide. So essentially, research objective 1 used Markov chain theory and the road network, so distance along the road network, to give us a measure of how accessible regions are. And this could be used on any set of regions connected by a road network. So that's the first research objective. and then remember that because it's going to come back at the end, basically. So research objective 2 then looked at the road network homogeneity, which is a measure of road network structure. And as I said in the beginning, spatial linear networks do have distinct patterns, and the pattern of a linear network is informative. For instance, it could tell us something about the accessibility. It could tell us something about the road network in general. And I've got these images on the slide. The one is the satellite imagery, and the other one is just the road network itself with the satellite imagery removed. And the green dots are just the midpoints of the roads. And here you see a formal kind of suburb area, and next to it an informal settlement. That's obvious from the satellite image, but it's also quite obvious, I want to say, from the road network itself. So the different patterns of the roads do actually tell you something about what's going on there beyond the road itself. What kind of neighborhood or situation are we looking at? So there's a lot of information there. And I specifically wanted to look at the homogeneity, which means essentially similar length and density across an area. Because in my mind, I would like a test, a statistical test, that would be able to tell me what I can see visually, that the top part of this image is a different neighborhood than the bottom part of this image. But there's no test for that. Well, there is now. But at the time that I started my PhD and this research, there was no test for it. So what did exist already at the time, was tests for the homogeneity of spatial point patterns. And that's why I decided, well, we can always represent a line pattern or a linear network by points. So specifically by midpoints. And what I'm not showing here in a lot of detail, but what I did do was to look at different ways of getting these points. I looked at taking endpoints, taking intersections, taking points at certain intervals along the roads. But the trade-off with computational complexity and modeling accuracy actually showed that the midpoints were informative enough, at least for these purposes. So there's some obligatory mathematics and statistics in fancy notation about road network homogeneity. So essentially homogeneity, and I'll start with the bottom line on the slide, which is that a point pattern is homogeneous if it has constant intensity across here is a specific two-dimensional space. And intensity is just defined as the average density of points per unit area. So essentially you want like a nice even spread of points across an area. That means it's homogeneous. And I just then applied that to the midpoints of lines, turned that into a spatial point pattern, and then checked to see whether it was homogeneous. Here's a little bit more information on the point pattern test, which was developed by Kromwinkel et al. And essentially what it came down to was taking a point pattern domain, dividing it up into quadrats, and then using the chi-squared goodness of fit test to see whether there's approximately an equal number of points per quadrat. The one thing that needed to be changed from a normal chi-squared goodness of fit test is that spatial point patterns, and by extension line patterns and road networks and things, are spatially dependent. So you can't just use the chi-squared test as it is, because that assumes independence, which isn't true. So what Kromwinkel did in the point pattern research was to just take bootstrap samples of 50% of the quadrats to break that dependence, and that worked quite well. So that's what we did. And one thing that I will note that will come back later is that there is a restriction on the number of quadrats. Automatically, we would think more quadrats is better, because then when you sample 50%, you get more different blocks that you can compare, and thereby break the dependence more effectively. But the chi-squared goodness of fit test does require that you have an expected number of at least 5 points per block, per quadrat. So that's the one restriction. And it's going to come back later, which is why I mention it now. So here's just the general methodology that I used I represented the road network as a line pattern. So which is the lines in a linear network, and then used that to generate a point pattern by simply taking the midpoints of each line, and then follow the point pattern methodology. All the information is here, but this point pattern methodology was developed by Kronwinkel, so it's not mine, unfortunately, because it's very cool. Wish it was mine. And then here's an example of how it works. I took a part of Mamelodi, which has different kinds of sort of formally developed road networks and informal road networks. These regions, the different colors here, I selected by hand or by eye. And I got the p-value. So the hypothesis here is whether or not it's homogeneous. And a smaller p-value when you reject the null hypothesis means that it's not homogeneous. And if you don't reject it, then it is homogeneous. So in this particular example, the overall area was inhomogeneous, which makes sense because we can see physically that there are formal suburbs and informal settlements in the same area. But then when I divided the different areas up with my intuition, looking at what seems to be a neighborhood, of course, I also used the satellite image for this, not just the road network, then they were homogeneous internally, which is great because that shows that the test kind of does what it's supposed to do. It will tell you, yes, this is one neighborhood, it's homogeneous, or, oh, these are different neighborhoods put together, that's inhomogeneous. And it was interesting to note also that informal roads also follow the rules of being internally homogeneous. Even though they're not planned by a central authority, people do tend to settle in more grid-like ways when there are no geographical restrictions, which in this part of the country, there really are not. It's flat and there are no huge lakes or rivers. So people are going to settle in a more sort of grid-like fashion. So in general, what I hope the test would do and what it did do was to show that inhomogeneity could suggest mixed settlement types or mixed neighborhoods, which was really the point of the test. That then flows into research objective 3, which is to cluster a road network. So all the work was done in research objective 2 to find a measure that will actually tell us, is this one neighborhood or is it not one neighborhood? Now the question becomes how to find these neighborhoods. And I'm just restating here that if you've got a homogeneous region, typically it will at least appear to consist of one neighborhood. If you've got a heterogeneous or non-homogeneous region, like on the right, you can see that that's at least 2 different neighborhoods. I mean, those road networks aren't even connected to each other. So the idea is to subdivide a road network into regions that are as internally homogeneous as possible. It's the same idea as something like k-means, where you want clusters that are internally homogeneous, but there's a lot of variation between the different clusters. That's exactly the kind of algorithm that I wanted for the road networks. So what I did was I started with k-means, network k-means, where you basically just use the distance on the road network instead of Euclidean distance. Network k-means plus plus. Remember that k-means plus plus is just k-means with a more sophisticated initialization. So it takes a bit less computation, a lot less computation, actually. So I started with an initial clustering, and then I started merging the initial clusters based on their homogeneity. And I will get to that in the next slides. Here, remember that I said that the number of quadrats would come back. Well, they're back. So the number of initial clusters was determined as the maximum number of areas or neighborhoods that the overall road network could be divided into. So as finely as possible, but still having expected number of points more than or equal to 5, so that we can actually use the chi-squared test, and by extension, the test developed in research objective 2. So here's a general flow chart of how the clustering algorithm worked. And I've got it explained in words on the next slide. So it's sort of the same The same thing for the visual learners and the more text-based learners, I suppose. So first of all, I would start off with a point pattern and the cluster labels as input. And then the final output would be the final list of clusters. And the cluster labels there are determined by the initial clustering. So the initial network k-means. Then I would get the convex hull on each cluster. And the convex hull is literally just if you take points and you draw the boundary around them. There's an illustration on the next slide. Basically, you just take the boundary around the points because then that becomes your observation window. Then I would run the test on each cluster, so on each of these little windows with points inside of it, and then obtain overlapping convex hulls where both contain homogeneous clusters, merge them. I know this is a lot of words, but there is an illustration on the next slide, and then I'll go through it again. Essentially, I would take each possible pair of like clusters next to each other. If they're homogeneous, merge them and check again if the merge is homogeneous. Because if it is, then probably those two clusters are both part of the same neighborhood. And eventually it stops when you can't merge anymore. Like if you take any pair of adjacent clusters and you try and merge them, you end up with inhomogeneity. Then the process stops. And here's an illustration. So on the left-hand side was the initial clustering. This was just obtained with network k-means because it's a nice algorithm to use. But of course, it doesn't take homogeneity into account. That's why I didn't just stop there. And these are the initial, so a bunch of initial clusters found by network k-means, and the gray lines around them are the convex hulls, or just like the smallest convex area that you can draw around those points. Then in the middle picture, that red area is obtained by taking the black and purple areas in the first image and merging them together. And again, taking the convex hull around them and testing to see whether that's homogeneous. And if it is, then we merge them. And then that would keep going step by step by step until the last image on the right-hand side, where this is the most homogeneous, most internally homogeneous clustering that you can get. So the blue area in the right-hand image sort of corresponds to those two green areas and the black area in the middle image. Those were part of the same neighborhood, as it turned out. So merging them together still resulted in something homogeneous. And that big green area was a bunch of road networks at the bottom that resulted in something that was pretty much homogeneous. And then the purple area, that's another area that's pretty much homogeneous. And if you merge any of these areas together, then they would become heterogeneous. So they are no longer the same neighborhood. So that's the sort of area that it ended, or subdivision of the region that it ended up with, which visually looks fairly good. Of course, this is sensitive to the initial clustering, but it does look fairly good. You can see that merging has been done. The final neighborhoods do generally make sense. Maybe the boundaries are a bit iffy, but they generally make sense. And that little cluster at the top, which is purple in the first two images and red in the last one, that one was never merged. And that's because it is heterogeneous to begin with. So it doesn't even consider any heterogeneous clusters for merging because they're already not homogeneous. Right, that was it for research objective 3. So essentially it turned out that this homogeneity clustering method, although it is quite sensitive to an initial clustering, given it's an okay initial clustering, will result in clustered areas that do correspond roughly to different neighborhoods, which is exactly what we want. And of course, it's unsupervised. So that's great. Then research objective 4 basically puts everything together. And that aim was to investigate the effect of road network structure, so specifically homogeneity, on accessibility using research objectives 1 to 3. And the overall methodology of this was to firstly subdivide a road network into homogeneous regions using the clustering method that I just presented. then model the accessibility between these regions using the accessibility model of research objective 1, and then to finally compare this to accessibility in another way of subdividing this road network. So see whether the homogeneity clustering regions actually give different accessibility results than something like administrative units. So here's the data. I looked at the western city of Tshwane. This was the old, these were the old boundaries of city of Tshwane before it expanded in, I want to say, 2011. I would have taken the whole municipality, but it just got really computational and I was on a time crunch because I wanted to finish my PhD. So I focused on the western area, which also is mainly the urban area. Of course, as you go more eastwards, it becomes more rural and further spread apart. So I also had a justification to focus on the more urban areas. And these images just show the road network, the road midpoints. Of course, it's quite dense, so it looks like just a bunch of areas, but those are all road midpoints. And then the wards, which are the administrative units on the right-hand side. So this image here shows how the homogeneity clustering worked. This specifically is a coarse clustering, which ended up with a grid size that you could have a grid of 4x4 on each of these units or more, but at least 4x4 quadrats. And so the first image shows the initial clustering, and then the middle image shows the results of the homogeneity clustering, and then the last one shows the tessellation of the results. Because as you'll recall from research objective 1, we needed to have this nice sort of jigsaw puzzle like the administrative units here. So with help from Lawrence Snyman in our geography department, who came up with a new way of how to get the overlaps to not overlap and how to fill in the gaps, I was able to turn the final clustering into a nice sort of jigsaw puzzle or partition. So that's the one regionalization, you could say. Then I did the same thing with a much finer clustering. Here I wanted 7x7 grid size. So on the left-hand side, there's the initial clustering. Then in the middle, there's the result of homogeneity clustering. And it does become, this is a limitation of the method. It does become a bit difficult on a very large area. It's most effective on smaller areas like the Mamelodi example that I showed earlier. But I repeated the same steps and got a nice sort of jigsaw puzzle at the end. And then here are the homogeneity results based on these two different, the coarser and the finer subdivisions. So there are some differences. I mean, you can see broad similarities towards the sort of top middle. There's a bit more homogeneity, and towards the bottom western side, there's a bit more homogeneity, and so on. So they broadly, they don't give wildly different results, which is good, makes sense. But they do give different levels of information. So in the coarse clustering, there were fewer like super homogeneous regions, but there were also fewer regions overall. And then in the finer clustering, there's more variation, perhaps more information about these neighborhoods, but there's also a lot more neighborhoods. So it sort of brings home the message that it's a user-defined result. So do you want a finer subdivision, which will give you more information, or do you want a more generalized area? And then I also looked at the accessibility, of course. The results I include here are the prominence index. There's more in the PhD, but just the prominence index, because otherwise there would be a lot of results to compare. Of course, I couldn't get homogeneity on the administrative units because they're not convex. But accessibility I could measure on all of them. And there it shows that there's some differences between them. So how you choose the subdivision, I mean, looking at the administrative units on the right-hand side, those two wards at the bottom there are in sort of Centurion area, and they are coming out as the most accessible. But then if you look at the fine clustering, there are some wards towards the sort of center northern parts of the municipality that come out as most accessible. And if you look at the coarse clustering, there's some at the bottom and on towards the east as well. So you essentially get different results of accessibility depending on how you select the regions, which is a useful result because it does show that how you choose the neighborhoods does influence accessibility. So then in conclusion, in this PhD, I developed a new computationally simple statistical model for interregional accessibility. I extended a spatial point pattern homogeneity test to work on road networks quite effectively. Then I used that test to develop an unsupervised clustering algorithm to identify homogeneous subdivisions of a road network. And then finally, I used that clustering algorithm to obtain two different subdivisions of the city of Tshwane municipality, at least the western part, and compared that to the administrative units. And it essentially showed that how you choose the regionalization, whether or not you take road network structure into account, and exactly how fine or how coarsely you do that has a pretty big impact on accessibility at the end of the day. And this does make sense. It corresponds to what's called the modifiable areal unit problem in geography, which is that if you look at different scales or different areas, you can expect different results, which is what we got as well. So there were some limitations to this. The accessibility model, of course, assumes that the Markov property holds for journeys traveling between wards, which might be an oversimplification, especially in complex road networks. Then, of course, the clustering method is very sensitive to the initial clustering. And then neither the accessibility model nor the clustering method look at edge effects. So that is something that could be explored and improved in future. I've got some future work. So the accessibility model, as I mentioned earlier, can be extended to account for traffic information, which is work in progress. Different initial clustering methods could be used for the homogeneity clustering method. And then they could both be improved for edge effects. And then in conclusion, well, the overall work is the first step. I would say not to diminish the work of my own PhD, but it was more of an exploration than a definitive final model. It's an exploration that needs to be done, a first step towards assessing accessibility within South Africa on a comprehensive scale. Because at this stage, a lot of the time it's being done at very like low level, regional level, municipal level if you're lucky. And of course, it's a country. All of these road networks and things talk to each other ultimately, and we need to understand the level to which people have access and where it can be improved to ensure a better future for everybody. So then I've got some references. These are just the main ones. My PhD had more than like 10 references, but these are the main ones that I used. And then I've got some. I'm not going to go into the coding techniques that I use because that is a whole separate seminar, but I have got some links, including my own seminar that I did on the SF networks package, which was how I analyze the networks. Very cool and useful stuff. And yeah, that's it. Any questions?
Thank you, Renate. Very interesting, of course, but I knew that. I want to add quickly on the SF networks. So the developer of SF networks is going to be at the South African Statistical Association conference at the end of the year, and we're hoping also that he has a visit at the University of Pretoria. So look out for that, which is quite interesting. Linda says, "Oh, he called you doctor. Look at that. Didn't even put it in inverted commas." Not yet, Linda. 2 weeks time. Okay. Anybody have any questions, comments, ideas? No questions are bad questions.
Sorry, can you hear me?
Yes, Lindy, go ahead.
I was just wondering, how could this be expanded towards like resources, let's say in like an informal settlement where let's say where taps are, or the ability to reach water or whatever, or maybe accessibility to let's say a grocery shop or something like that. Could it be expanded, or is this only, like, I want to say, fixed on road networks?
So the idea behind this is that the accessibility is via the road network. So if you have specific destinations in mind, as long as they're connected by the road network. So you couldn't extend this for accessibility to, let's say, a location within a field. You could only extend it to the accessibility to the field itself. And then if there are no roads inside the field, maybe there's a tap or something inside the field. Well, we'll only know the accessibility of the field. So it can be extended to specific locations or things, but they have to be on the road network, basically. Otherwise, the best guess that we can do is, okay, up to the closest point on the road network. And from there, you need to find your own access across the field.
It's a nice question, Lily. Monette says in the chat, Renate, very cool. So I assume this could, of course, be extended to a countrywide accessibility network, and maybe even in the travel industry to create something like an ideal route for travel.
Yes, yes, absolutely.
The ideal route for travel, I suppose, in the terms of question, sorry for the dogs, accessibility.
Yes, well, it would be the optimal route. We are actually working on some road optimization. So that would be the optimal travel route in terms of, the only thing that my model at the moment can do is distance, but we want to incorporate things like traffic, maybe slope, whatever is relevant. It depends as well on, if you're looking at something like countrywide, then travel cost, some sort of comprehensive travel cost is necessary. If you're looking at a smaller region within, let's say, an informal settlement, you probably want to take geographical factors like slope into account.
Sorry, I have another question. How could this reach out to Google Maps? Because obviously they also do road optimization. And so what do they use? Because obviously it's really working. And if this is like a new thing that you have now, or new connections that you have created, will this improve on Google Maps, or is this just a different approach to what they're already doing?
So I would say in a sense, both. It is, of course, Google Maps has a ton of resources. So I don't know exactly what they're doing because it's all proprietary, but they will be doing something similar, just perhaps more focused on the road network rather than the regions. The big thing is that they don't take informal roads into account. And this isn't something that I spoke a lot about in today's presentation, but there is a sort of a strong theme of informal roads throughout my research as well. So that's the one sort of improvement that we could do, is to say, well, there are roads that are not officially on the system, and that's something that we do look at, that they don't.
I also think that possibly the Google Maps doesn't, sorry, Liddy, Google Maps might do routine, but I don't think they have formal indices of accessibility or necessarily.
No, they don't. Yeah.
Sorry, Liddy, go ahead.
Yes. Sorry, no, because I just wanted to say, because Google Maps, all I know is they use a lot of the mapping cars that the most drive around. And so that is obviously very based on how accessible something is. So this could actually help, because you're using satellite mapping. It could be an improvement on that side, especially like hikes and stuff like that. Okay, that's pretty cool. Thank you.
Nice point. I see Amy says in the chat as well, Renata, would it be possible to consider road condition as well? An informal road not made of tar could be very difficult to drive on if it rains a lot, thus making it less accessible during rainy season as opposed to dry season.
Yes. So Amy, what you should do is sit in the meetings with Charlotte and Renate, because we're actually looking at bringing in other factors. That's a very, very good point to look at the seasonality as well of something like a dirt road. Very, very good point. But yes, anything sort of like road condition, slope, and well, the raininess is included in road condition, but yes.
Deterioration of roads. Yeah. Any other questions, comments, ideas of what Renate should do next? She's got nothing to do now because she's finished her PhD. So you just need to give her tasks to do now. Okay, I don't see any more comments. I don't see any hands up. Okay, so Renate, thank you so much. And congrats again on all your hard work. When you show it like this, it looks like it just went chuk, 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 you know,
Yeah.
and it was so straightforward and easy. But you and me know that you worked really, really hard. So congratulations.
And
on
like
that.
half of your job was to talk me off the edge of like despair, because this is never going to come together as a
That's
PhD.
it. And I see Pravesh, the co-supervisor, is also clapping his hands there for her. So absolutely. And I hope that if we've got some students here in the audience, that they can now see their path into their PhD as well. It's a good path to go. You work hard, but nothing is, you don't get anything good if you don't work hard. So you can do really cool research. So thank you, Renate. And please keep your eye out for our future seminars, and hope to see you soon. Have a wonderful day, everybody. There's another question from Amy. Renate.
Yes.
Is this only applicable to South African road systems because it be applied to other countries?
Anywhere in the world. You would have to, when you look at things like how you calculate road condition and that kind of thing, you might look at different things. So you might be dealing with the Netherlands, where you won't be looking at informal roads. There'll be some like small tweaks, but the overall methodology works anywhere.
Yeah, absolutely. Nice question, Amy.
All
right, everybody. Have a lovely day.
Goodbye. Right, bye.